Okay, you guys, so today we're going to work on 4.1. This is kind of the beginning of the newer material. Like I said, you've all probably seen polynomials, but we're going to do a little bit different stuff with it. So we're going to identify polynomials and their degree. That's the first thing we'll talk about. So I just want to kind of show you guys when they say polynomial, this is what they mean. It has to be able to be written in the form a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub 1 x plus a sub 0. And this is a standard way to write a polynomial function. And basically what it means is that when we're writing polynomials, all the powers are nice and clean, okay? So the n has to be a whole number. It can't be negative, it can't be fractional, we can't have rational exponents. Polynomials, n is a very nice value, so meaning nice powers, and then the a sub n is just whatever term we're on, the first term, second term, third term, so on and so on and so on. So the main thing for you guys is polynomials have to have exponents that are whole numbers, okay? No negative exponents and no rational exponents allowed, or decimal exponents. And one of the things about polynomials is they're very smooth, they have nice behavior, so we really like them in mathematics, okay? So if we want to identify a polynomial, I could give you 5x cubed minus 1/4 x squared minus 9 equals g of x, and I would say, yeah, that's a polynomial. Yep, polynomial, because it has nice powers. All the exponents are clean. There's nothing strange going on. Now let's look at another one. G of x equals the square root of x. Okay, so that means that g of x, if we wanted to write it as a radical or write it as an exponent, it's actually x to the 1/2. That's the same as the square root. So we know this is not a polynomial. And then we could take a look at this one, h of x equals x squared minus 2 all over x cubed minus 1. And we can tell just by looking at this. Now, the strange thing is, this is actually a polynomial, and this is actually a polynomial. But when you have a polynomial divided by a polynomial, you get a rational expression or a rational function, and it is not a polynomial itself. So we would say not a polynomial, okay? This one, let's look here. Let's say that I have, I want to find the degree of a polynomial. So the degree of a polynomial is found in this fashion. So let's say that we have 7x to the 5th plus 2x squared minus 3x plus 1. And let's say that this is f of x. Then f of x has a degree of 5. So the degree is always based on the biggest power. So what is the biggest exponent in the polynomial? That is how we find the degree, okay? So then if I had g of x is equal to 1 plus 2x minus x to the 5th, or not say x to the 5th, x to the 4th, then we would say degree 4, okay? Now, there's a little bit slightly different problem, where if we had x squared y to the 3rd plus 2xy, well, this would be a polynomial expression. This would be this would have a degree of 5, okay? Because 2 plus 3 is 5. So when you have different variables involved, the polynomial, or again, this isn't really something we're going to work with too much in this class, but the degree is the combination of the two powers. Normally you can't combine powers unless the bases are the same and you're multiplying. Well, we're multiplying, but the bases aren't the same. So we're not actually saying that the power of x is 5 or that the power of y is 5, but we're saying if we wanted to classify this, this would be degree 5. Okay, so let's move on from there. Okay, one little thing, little quick note, we're going to talk about this later on. So we have something called a power function. And all a power function is something that takes on this form. okay, where it's a x to the n, where n could just be any, whole number. So we often refer to these as power functions. That'll come up a lot in Calc 2 when we talk about power series. So a series that's generated from a bunch of these types of functions. So we'll talk about that later on. We'll do a little bit with it this semester. We'll use it to help us determine end behavior, things like that. But in general, power function is just kind of like a nice, clean version. Okay, and it's something we'll spend a little more time on, okay? So just kind of put this in the back of your mind for now. We'll talk about it a little bit later, but we're not going to go too heavy into that right now. So the second thing I really want to talk about is transformations. So the thing is you've kind of already done this, right? Because technically, if I told you that f of x is equal to x minus 2 quantity squared plus 1, now this is a parabola, right? Now a parabola is in fact a function, okay? But it's a special type of function. It is also a polynomial. It's just a polynomial that we work with so much that we gave it a special name. You guys already know how to graph this. You transform it, you move it over 1, 2, and then you move it up 1. You put a dot, and then you draw your parabola. So you already know how to do transformations on polynomials. So I want to give you one that's a little bit different than a parabola, but it's still a polynomial. Let me see here. Let's say we have f of x equals 1 minus x to the 5th, okay? So let's look at the base function, the power function of this. So let's say that we look at the parent function, okay? Or we compare it to its power function, okay? And we would say some p of x is equal to x to the 5th. This guy is a manipulation of this. So what I'm going to do is I'm going to do a graph for, oops, I don't know why those doesn't. I'm going to do a graph for this. Okay, and from here, I'm going to graph the basic x to the 5th. Okay, so the basic x to the 5th function, if we put this in our calculator, looks something like a cubic. It's just a little bit steeper, okay? I didn't draw it perfect, but that's basically what it would look like, okay? So that would be y, or p of x equals, no, I'll just say y. Y equals x to the 5th. So what we want to do is we want to think about what would putting a negative in front of that do. So we're going to now take that same function and we're going to put a negative in front of it. So that's going to make it flip and it will become this. That function. And again, you guys can take out your calculators. Feel free to take out your calculator, go to y equals, and then do negative x to the 5th. And when you graph it, you get something like that, okay? So this would be y equals negative x to the 5th. But they asked me for negative x to the 5th with a plus 1. So I'm going to draw this, okay? And then I'm going to say negative x to the 5th. So I'm going to draw the same one, but I'm going to shift it up 1. So normally I would intersect here, so I'm going to shift up here. I'm going to draw the same drawing, or try to draw the same drawing, and that is y equals 1 minus x to the 5th. I shifted it up 1. So you can do transformations on polynomials just like you guys have done before. It's really not a big deal. Let me give you guys one to kind of work on yourselves. So let's come over here. Suppose I gave you g of x is equal to 1/2 x minus 1 to the 4th. So what is the power function that's associated with this? So the power function that's associated with x minus 1 to the 4th is this is going to look somewhat similar to this guy. This is y equals x to the 4th. Now it's not a parabola, but it kind of looks like one. So this is y equals x to the 4th. Because this, if I FOILed this out, I would get an x to the 4th. So in the previous videos, I called it a parent function. So what this is saying is if you FOILed this polynomial out, the biggest power would be x to the 4th. So it's going to kind of take on some behavior like x to the 4th at certain angles, at certain aspects of it. So basically, that's y equals x to the 4th. I'm going to come over here. I'm going to draw another one. And this time I'm going to do y equals, let's do it in blue, y equals x minus 1 to the fourth, which you guys know is a shift to the right of 1. So I'm going to go over 1, and then I'm going to draw the same drawing. And it's a little bit wider than the parabola. I don't know why I drew it like that. It's a little bit wider than the parabola. Okay, so that would be y equals x to the fourth. Now we have to do it with 1/2. So let's draw another one. And now we're going to come over here and we're going to do y equals, you know what, maybe I should put it up higher. Y equals 1/2 x minus 1 to the fourth. So now that means it's going to be vertically compressed even more than before. So all that stuff you learned with parabolas still carries over to these other power functions. Okay, so now we're going to do this, and it's going to be even wider than before. We're still here at 1, and this time it's going to be even wider than before. I kind of over-exaggerated it, but you guys get the idea, okay, because it's vertically compressed versus vertically stretched. Okay, so this is, again, all the stuff you guys have learned from transformation still works. You can apply it to other things, especially when it comes to polynomials. And it's not just polynomials. Everything seems to, you know, whether it's exponentials, logarithms, they all kind of have this behavior that you can shift them left, shift them right, even trig functions. It works the same. Okay, so that's just a kind of a background on that. Okay. So let me do the third thing I want to talk about is real zeros. Okay, so real zeros, let me write you a little definition here. If f is a function and r is a real number for which f of r equals 0, then r is called a real zero of f. Okay, so here's the thing. You've already been doing this your whole life. If you're at this point in math, you've definitely done this before. You guys often talk about factors. They help us find the real solutions to f of x equals 0. You often talk about them as x-intercepts, and now we're calling them the real zeros. So basically all these things I mean, there's other ways to think about it, but in general, when I'm talking about x-intercepts, I'm talking about real zeros. When I'm talking about the solutions to f of x equals 0, I'm talking about real zeros. When I ask you to factor something and set it equal to 0, I'm talking about the real zeros. So you've been doing this all along, but they may not have called them the real zeros, okay? So these are all things that you already have been doing. It's just now you want to associate x-intercepts with real zeros, with factors, with solutions. They're all similar, okay? So let's see here. Let's talk about multiplicity. Okay, so multiplicity. Multiplicity basically means how many times that factor appears in the solution to f of x equals to 0, okay? So how many times the factor appears, or the solution, the real zero, appears in f of x equals to 0, okay? So let me give you an example. So let's say that I have x plus 2 cubed times x minus 1 squared times x to plus 5 to the 7th, okay? And let's say this equals p of x, okay? What this means is x plus 2 equals 0 means x equals negative 2. This has a multiplicity of 3 because it appears 3 times in the polynomial, okay, in the factors. So over here we have x minus 1 equals 0. That means that x equals 1 oops, x equals 1. This has a multiplicity of 2, right? And then let's do one more. X plus 5 equals 0. This means that x equals negative 5. This has a multiplicity of, you guessed it, 7. Okay, so once again, all multiplicity means for, now it implies a lot, but it basically is saying how many times that 0 occurs, or basically the factor, how many times that factor occurs, okay? And there's some information you can get from multiplicity, okay? So let's look at some info from multiplicity, okay? Let me just see this. So if R is a 0 of multiplicity, of even multiplicity, sorry about that. Of even multiplicity, then the polynomial bounces off the x-axis, okay? Then we have if R is a 0 of odd multiplicity, then the polynomial goes through, or passes, let's say passes through, that sounds fancier. Polynomial passes through the x-axis, okay? So if it has a multiplicity that is even, it's going to bounce off the x-axis. If it has a multiplicity that is odd, then it's going to pass through the x-axis. And let me show you what I mean. So you guys know that if I gave you p of x is equal to this parabola, x minus 1 quantity squared, let's just say x minus 1 quantity squared, okay? So then if I do this, that means technically, right, that it's x minus 1 times x minus 1. That means that x equals negative 1 has a multiplicity of 2 because it occurred 2 times, right? It happened twice, all right? So what we're going to do is we're going to graph this. I'm going to shift my graph over 1 to the right, and then I'm going to graph it. And look what it does. It bounces off the x-axis, okay? So that's what it means by bounces off, okay? Now, when they say passes through, let's say that I have p of x equals, x cubed. Yeah, let's just say x cubed. That means that it has x equals 0, but how often that it occurs, it has a multiplicity of 3. So it has a multiplicity that is odd. This has a multiplicity that is even. So according to this one should bounce, which it did. That one bounced. And now let's look at this one. Well, we know that x cubed looks like this. Look what it did at the 0. So right here, where it had its real 0 of 0, it went right through it. It did not bounce, and that's because it had odd multiplicity. So these are things that you learn about multiplicity and polynomials. So we're going to learn a lot of background information. Hopefully you can watch this video and some of the other ones and then ask me questions before the exam, and then we'll go from there. So that's how you can use multiplicity to help you, okay? So now, and again, a lot of this section is about just by looking at something, you can extract a lot of information. So we can already do that for polynomials that are of the quadratic form, okay, that are parabolas. But now we want to be able to do it for pretty much any polynomial just by looking at the powers and looking at the relationships, looking at the power function, looking at end behavior. We can start almost having a picture of it before we even draw it on our calculator or graph it on our calculator. So, turning points. Okay, so turning points. A polynomial has oops, hold on, a polynomial of degree n has at most n minus 1 turning points. And you'll see that in the homework. So if you have a fourth degree polynomial, meaning like x to the fourth plus x cubed, the most that it can turn, the most that it can do, you know, something like this, the most that it could do, let's see, here's 1 turning point, here's 2, here's 3, here's 4. So that means that this could not be a fourth degree polynomial. This would have to be a fifth degree polynomial or larger, because you always have to have 1 less turning point than you have degrees. Now, that's not to say that if you have a seventh degree polynomial, it has to have 6 turning points. It may only have 2. It just really depends on the setup. But what this is saying is it has at most n minus 1. So if you have a fifth degree polynomial, the most amount or the largest amount of turning points you could have is 4. Okay, it doesn't mean you have to have 4, but you could have 4. Okay, so that's something to keep in mind. Then we have end behavior. Okay. For large values of x plus or minus the graph. So for large value of x, whether they're positive or negative, the graph of the polynomial will resemble the graph of its power function. So just like if I had this, if I had f of x equals x to the fifth plus 2x squared plus x minus 1, and then over here I had g of x equals the power function x to the fifth, okay? Oops. What this is saying is the way that this function behaves at the end of the day, okay? So I'm going to graph x to the fifth on my calculator. Y equals x to the fifth plus 2x squared, I probably shouldn't have done so many of these, plus x minus 1. So this guy looks something like this. And then it does something like that, okay? So that's what f of x looks like, okay? Now what this is saying is that when I come over here and graph this guy, the way that it ends, the way that it behaves, where it approaches negative infinity on the left and positive infinity on the right, that's how this will behave also, because the parent function gives its, almost like its guidelines to the other functions. So let me graph this guy. So this guy does one of these. So notice the way this one is going to end when we come way over here, and the way this one is going to end when we come way over here, this is approaching positive infinity. This is approaching negative infinity in terms of height. Look at this. This is approaching negative infinity, and this is approaching positive infinity, right? So they have the same behavior, and it's all based on the power function. So that means when I tell you x to the seventh, if you know what x to the seventh already looks like, then whatever I give you, x to the seventh plus 2x to the fifth plus 3x squared plus 8, you know that how it'll end. You don't know what happens in the middle. So all kinds of stuff can happen in here. All kinds of stuff can happen in here. But at the end of the function, you know how it's going to behave. It's going to approach negative infinity or positive infinity, or whatever the case may be. Okay. Think about it like this. Think about if I gave you the basic function f of x equals x squared plus 2x minus 5. Let me graph this in my calculator real quick. Let's do x squared plus 2x minus 5. Okay, so this guy, I'm just sketching here. I'm not trying to be really accurate. This guy does this. right? So look at the end behavior. For this, it's approaching positive infinity over here, and it's approaching positive infinity there, okay? Now let's graph its power function representative. G of x equals x squared. Well, we already know what that looks like. That's a parabola that does this. Oops. Right? But once again, look at the end behavior. Infinity, infinity. So that's what it's saying, is if you know the base polynomial, the parent function or the power function, then you can talk about the behavior at the end of the day for the other function. So that's kind of the power of the power function, okay? Okay, so hold on real quick. Let me make sure I covered everything I wanted in that. Okay. So let's maybe take and let's just kind of recap what we've done so far. Okay, so let's take this function, f of x equals two x plus 1, x minus 3 squared. Okay, so now we're going to talk, I want to find the end behavior. I also would like to find the x and y intercepts, just, you know, extra information we should be able to find. I also like to find the zeros and their multiplicities. Okay. And I'd also like to graph it on the calculator. And we'll go from there. All right, so let's see what we got here. Oh no, there's more. Sorry about that. Graph on the calculator, step 5. Let's find the approximate turning points. And we're not exactly sure what they are because we're going to have to use our calculator to find these. In Calc 1, I will teach you how to find these turning points by hand, but for now we're going to have to approximate the turning points on calculator. Okay, now step 6, I want to graph this by hand. Obviously I know what it looks like on the calculator already, but I want to try to graph it by hand. So we're going to have this, and then I want to find my domain. And then I want to find my intervals of increasing and decreasing. I don't know why I abbreviated one and not the other. Intervals of increase and decrease. Okay, so a lot of information that we should be able to take now that we know multiplicity. We've already know how to do x and y intercepts. We know how to find the zeros. We know how to graph it on our calculator. The turning points will be a little weird, but let's give it a shot. Okay, so now let's come up here. Now, what is this end behavior related to? Well, now think about it. This is similar. If we FOILed this out, again, I don't know exactly. I don't want to FOIL all of it out. But if I squared this, wouldn't I get x squared? And at some point, it's going to multiply by 2x. So I'm going to get 2x cubed, okay? And then it'll be plus, and then I really don't care what happens after that. So to me, the power function it's related to is, let's call it p of x for power function, is going to be 2x cubed. So it will behave like this, okay? So 2x cubed has behavior like this, right? I don't know what happens in here, right? I'm not saying I know what happens in there, but what I am saying is that here and here, I know it's going to go to negative infinity, and I know it's going to go up to positive infinity, okay? So that's all I'm saying. X-intercepts, you guys know how to find the x-intercepts. You let y equals 0. So let's come up here. And that means we have 0 equals 2x plus 1 times x minus 3 squared. So we know that x equals negative 1/2 and x equals 3, right? So these are the x-intercepts. I'll write them as actual coordinates. -1/2, comma 0, and 3, comma 0. These are my x-intercepts. Okay, now we'll come over here, and for our y-intercepts, let x equals 0. So then when I come up here to this function, I'm going to put a 0 in for x, and I'm going to put a 0 in for the other x, and I should have, what, -3 times -3. So I'm going to say that we have f of 0 equals 1 times 9, right? Because -3 squared is 9. So we should get 9. So then that means our intercept is 0, comma 9. That's our y-intercept. Okay, so we have our x-intercept, we have our y-intercept, so we have a lot of stuff we can draw with now. So now we're going to come over here. We know that our zeros, we already found them. We said that x equals -1/2, and we said that x equals 3. This has a multiplicity of 1. This has a multiplicity of 2, right? Because 3 happened twice, right? Because of the squared. And this had only a first power right here. They don't write it, but it was a first power. So when I go to find multiplicity, it was 1 and 2. This is even multiplicity. This is odd multiplicity. Okay. So now I'm going to graph it on my calculator just to kind of get a rough idea of what I'm supposed to be getting into. And we're going to need that to approximate. So let me graph this guy. Parentheses 2x plus 1. And then x minus 3, close parentheses, squared. Okay, so now I'm going to graph this guy. Oh, that's not good. I don't know why my calculators have been causing so many problems. I had to change the window a little bit. It's going off the screen. There we go. Okay, so let me make sure I entered it in right and I didn't make another silly mistake. 2x plus 1, x minus 3, quantity squared. Yep. So the graph I get looks something like this. Somewhere up here it crosses. It comes down. And then somewhere right here it bounces. Wonder why that is, right? And then it goes up forever like that, okay? And again, we kind of know this is going to happen because we already know the end behavior is supposed to behave like this. On the left side, it goes down to -infinity, and on the right side, it goes up to +infinity, okay? So here's what I want you guys to do on your calculator. So while you're on this graph, go to second function, calculate, okay? So second function, calculate. And I want you to find the turning point. So we need to find this guy. So this guy right here would be a maximum. So let's find the maximum right there. So I'm going to go a little to the left and a little to the right, and I hit answer. And it says that the approximate turning point is, oops, for the first one would be 2/3 because it gave me 0.666665. So I'm assuming it's 2/3. And then the other one is 12.7037. So I'm going to say about 12.7. Okay. So that's my approximate turning point. Okay. Now we got to find this other one right here. So what I'm going to do is I'm going to go to second, calculate again, but that one is going to be a minimum. So I'm going to get close to it. I actually already know what it is, but I'm just going through the steps. So I get 3 and basically 0, okay? Now, we kind of already knew that because look right here. This says that one of the zeros is 3, okay? This says that one of the zeros is 3, okay? And this guy looks like he goes right through 3, okay? So And again, I get 2.62 times 10 to the negative 13 for my height. So that's basically 0. Okay, so I'm assuming that it's some rounding in there. So we're going to say that this other turning point is going to be 3, 0. Okay, so let me see here. That sounds good. So now I want to try to graph. So I know that I have a 0 at negative 1/2. So if this is 1, negative 1, 2, 3, 4, you know, I probably shouldn't have such big numbers. 2, so I should make that negative 2, negative 1, negative 2, negative 3, so on. 1, 2, 3, 4, 5, 6, 7, 8, so on. 2, 4. We have to do this one by more. Otherwise, we won't make it. Okay, so I know that I'm going to cross at 3, or I'm going to bounce at 3, 0. I know I have to end up over here, right? I know I have to end up right there because of the end behavior. And then I know that I'm going to turn here. So maybe I need to curve this a little. I have a turning point after this at 2/3, 12.7. So here would be 2/3. Here's about 12.7, 2/3, right? So now this has to, let me do this a little better. So this, oh, and then we know our y-intercept. Actually, we know a lot. Hold on, I forgot we had the y-intercept as well. The y-intercept is 0, 9. So that's going to be right here, 0, 9. And then we know we have an x-intercept at negative 1/2, 0. So that's going to be right here. So I have it. Okay, so that's my graph. And now let's look what we saw in the calculator. Pretty darn close. So we did that. And how did I know it was going to bounce right here? How did I know it was going to bounce right there? Because it had an even multiplicity. How did I know it was going to go through right here? Because it had an odd multiplicity. So these are things I know. Now let's look at domain, nice and easy. Negative infinity to positive infinity, no problem. Intervals of increasing to decreasing. Well, I know that it's increasing from here to here, right? All the way up to my turning point. And that turning point, let's do from the x values. So that turning point was 2/3. So let's say that from negative infinity to 2/3, it was increasing. And you know what, I think there's another one that's also increasing. Union from 3 to infinity. So this is increasing. And then so decreasing is from 2/3 to 3. Decreasing. Oops. Okay. So this is how we can answer all of these questions, right? And again, the goal is that we can kind of use our calculator with technology along with information that we already know to help us gain a deeper understanding of polynomials and how they work. Okay. By the way, it was a 5th power. No, I'm sorry. It was a 3rd power because this is a squared and this is a 1. So if I FOILed all that out, I got a power function that was cubed. So that means it could have at most 3 minus 1 turning points, which is 2. And as it turns out, it did have 2, one right here and one right here. Those are the 2 turning points. Okay. So hopefully that helps you guys get started on 4.1. I'll be releasing another video in a little bit, hopefully, that will help you get started on more information. Okay, but that'll do it for this section. Thanks for watching the video, you guys, and good luck with the homework.